Part 1 of the Mathematical Appendix to Principles of Economics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This reading by Carl Manchester 2008. Principles of Economics by Alfred MARSHALL. Mathematical Appendix. Note 1. The law of diminution of marginal utility may be expressed thus. If U be the total utility of an amount X of a commodity to a given person at a given time, then marginal utility is measured by the differential of U over the differential of X multiplied by the change in X, while the differential of U over the differential of X measures the marginal degree of utility. Jevons and some other writers use final utility to indicate what Jevons elsewhere calls final degree of utility. There is room for doubt as to which mode of expression is the more convenient. No question of principle is involved in the decision. Subject to the qualifications mentioned in the text, the square of the differential of U over the differential of X squared is always negative. Note 2. If M is the amount of money or general purchasing power at a person's disposition at any time, and mu represents its total utility to him, then the differential of mu over the differential of M represents the marginal degree of utility of money to him. If P is the price which he is just willing to pay for an amount X of the commodity which gives him a total pleasure U, then the differential of mu over the differential of M multiplied by the change in P equals the change in U, and the differential of mu over the differential of M multiplied by the differential of P over the differential of X equals the differential of U over the differential of X. If P' is the price which he is just willing to pay for an amount X' of another commodity which affords him a total pleasure U', then the differential of mu over the differential of M multiplied by the differential of P' over the differential of X' equals the differential of U' over the differential of X', and therefore the differential of P over the differential of X such that the differential of P' over the differential of X' is equivalent to the differential of U over the differential of X such that the differential of U' over the differential of X'. Compare Jevons' chapter on the theory of exchange. Every increase in his means diminishes the marginal degree of utility of money to him. That is, the square of the differential of mu over the differential of M squared is always negative. Therefore, the marginal utility to him of an amount X of a commodity remaining unchanged, an increase in his means increases the differential of U over the differential of X divided by the differential of mu over the differential of M, i.e. it increases the differential of P over the differential of X, that is, the rate at which he is willing to pay for further supplies of it. We may regard the differential of P over the differential of X as a function of M, U and X, and then we have the square of the differential of P over the differential of M times the differential of X, always positive. Of course, the square of the differential of P over the differential of U times the differential of X is always positive. Note 3. Let P and P' be consecutive points on the demand curve. Let PRM be drawn perpendicular to OX, and let PP' cut OX and OY in capital T and lowercase t respectively, so that P'(R) is that increment in the amount demanded which corresponds to a diminution PR in the price per unit of the commodity. Then the elasticity of demand at P is measured by P'(R) over OM divided by PR over PM, i.e. by P'(R) over PR times PM over OM, i.e. by Tm over PM times PM over OM, i.e. by Tm over OM, or by P capital T over P lowercase t. When the distance between P and P' is diminished indefinitely, PP' becomes the tangent, and thus the proposition stated on page 103 is proved. It is obvious a priori that the measure of elasticity cannot be altered by altering relatively to one another the scales on which distances parallel to OX and OY are measured, but a geometrical proof of this result can be got easily by the method of projections. While analytically it is clear that the differential of x over x divided by the negative of the differential of y over y, which is the analytical expression for the measure of elasticity, does not change its value if the curve y equals function of x be drawn to new scales, so that its equation becomes qy equals the function of px, where p and q are constants. If the elasticity of demand be equal to unity for all prices of the commodity, any fall in price will cause a proportionate increase in the amount bought, and therefore will make no change in the total outlay which purchasers make for the commodity. Such a demand may therefore be called a constant outlay demand. The curve which represents it, a constant outlay curve, as it may be called, is a rectangular hyperbola with OX and OY as asymptotes. There is some advantage in accustoming the eye to the shape of these curves, so that when looking at a demand curve one can tell at once whether it is inclined to the vertical at any point at a greater or less angle than the part of a constant outlay curve which would pass through that point. Greater accuracy may be obtained by tracing constant outlay curves on thin paper, and then laying the paper over the demand curve. By this means it may, for instance, be seen at once that the demand curve in the figure represents at each of the points A, B, C and D an elasticity about equal to 1. Between A and B, and then again between C and D, it represents an elasticity greater than 1, while between B and C it represents an elasticity less than 1. It will be found that practice of this kind makes it easy to detect the nature of the assumptions with regard to the character of the demand for a commodity, which are implicitly made in drawing a demand curve of any particular shape, and is a safeguard against the unconscious introduction of improbable assumptions. The general equation to demand curves representing at every point an elasticity equal to n is the differential of x over x plus n of the differential of y over y equals 0, i.e. xy to the power n equals c. It is worth noting that in such a curve the differential of x over the differential of y is equal to the negative of c over y to the power n plus 1. That is, the proportion in which the amount demanded increases in consequence of a small fall in the price varies inversely as the n plus 1 nth power of the price. In the case of the constant outlay curves, it varies inversely as the square of the price, or, which is the same thing in this case, directly as the square of the amount. Note 4. The lapse of time being measured downwards along OY, and the amounts of which record is being made, being measured by distances from OY, then P' and P being adjacent points on the curve which traces the growth of the amount, the rate of increase in a small unit of time n is ph over P-n equals ph over P-h multiplied by P-h over P-n equals Pn over n lowercase t multiplied by P-h over P-n equals P-h over n lowercase t, since Pn and P-n are equal in the limit. If we take a year as the unit of time, we find the annual rate of increase represented by the inverse of the number of years in n lowercase t. If n lowercase t were equal to c, a constant for all points on the curve, then the rate of increase would be constant and equal to 1 over c. In this case, minus x multiplied by the differential of y over the differential of x equals c for all values of x. That is, the equation to the curve is y equals a minus c log x. Note 5. We have seen in the text that the rate at which future pleasures are discounted varies greatly from one individual to another. Let R be the rate of interest per annum, which must be added to a present pleasure in order to make it just balance a future pleasure that will be of equal amount to its recipient when it comes. Then R may be 50 or even 200% to one person, while for his neighbour it is a negative quantity. Moreover, some pleasures are more urgent than others, and it is conceivable even that a person may discount future pleasures in an irregular, random way. He may be almost as willing to postpone a pleasure for 2 years as for one, or on the other hand he may object very strongly indeed to a long postponement, but scarcely at all to a short one. There is some difference of opinion as to whether such irregularities are frequent, and the question cannot easily be decided. For since the estimate of a pleasure is purely subjective, it would be difficult to detect them if they did occur. In a case in which there are no such irregularities, the rate of discount will be the same for each element of time, or, to state the same thing in other words, it will obey the exponential law. And if h be the future amount of a pleasure of which the probability is p, and which will occur, if at all, at time t, and if R equals 1 plus lowercase r, then the present value of the pleasure is ph R to the power of minus t. It must, however, be borne in mind that this result belongs to hedonics, and not properly to economics. Arguing still on the same hypothesis, we may say that if π be the probability that a person will derive an element of happiness, delta h, from the possession of, say, a piano, in the element of time, delta t, then the present value of the piano to him is π by R to the power minus t times the differential of h over the differential of t times the differential of t, for values between 0 and T. If we are to include all the happiness that results from the event at whatever distance of time, we must take t equals infinity. If the source of pleasure is, in Bentham's phrase, impure, the differential of h over the differential of t will probably be negative for some values of t, and of course the whole value of the integral may be negative. Note 6. If y be the price at which an amount x of a commodity can find purchasers in a given market, and y equals function of x be the equation to the demand curve, then the total utility of the commodity is measured by function x by the differential of x, for values between 0 and a, where a is the amount consumed. If, however, an amount b of the commodity is necessary for existence, the function of z will be infinite, or at least indefinitely great, for values of x less than b. We must therefore take life for granted, and estimate separately the total utility of that part of the supply of the commodity which is in excess of absolute necessaries. It is, of course, the function of x by the differential of x for values between b and a. There are several commodities which will satisfy the same imperative want, as for example water and milk, either of which will quench thirst. We shall find that, under the ordinary conditions of life, no great error is introduced by adopting the simple plan of assuming that the necessary supply comes exclusively from that one which is cheapest. It should be noted that, in the discussion of consumers' surplus, we assume that the marginal utility of money to the individual purchaser is the same throughout. Strictly speaking, we ought to take account of the fact that if he spends less on tea, the marginal utility of money to him would be less than it is, and he would get an element of consumer's surplus from buying other things at prices which now yield to him no such rent. But these changes of consumer's rent, being of the second order of smallness, may be neglected, on the assumption which underlies our whole reasoning, that his expenditure on any one thing, as for instance tea, is only a small part of his whole expenditure. If for any reason it be desirable to take account of the influence which his expenditure on tea exerts on the value of money to him, it is only necessary to multiply the function of x within the integral given above by that function of x by function x, i.e. of the amount which he has already spent on tea, which represents the marginal utility to him of money when his stock of it has been diminished by that amount. Note 7. Thus if A1, A2, A3, and so on, be the amounts consumed of the several commodities of which B1, B2, B3, and so on are necessary for existence, if y equals function 1 of x, y equals function 2 of x, y equals function 3 of x, and so on, be the equations to their demand curves, and if we may neglect any inequalities in the distribution of wealth, then the total utility of income, subsistence being taken for granted, might be represented by the sum of the function of x by the differential of x for values between b and a. If we could find a plan for grouping together in one common demand curve all those things which satisfy the same wants and arrivals, and also for every group of things of which the services are complementary. But we cannot do this, and therefore the formula remains a mere general expression, having no practical application. Note 8. If y be the happiness which a person derives from an income x, and if, after Bernoulli, we assume that the increased happiness which he derives from the addition of 1% to his income is the same whatever his income be, we have x by the differential of y over the differential of x equals k, and therefore y equals k log x plus c, when k and c are constants. Further, with Bernoulli, let us assume that A being the income which affords the barest necessaries of life, pain exceeds pleasure when the income is less than A, and balances it when the income equals A. Then our equation becomes y equals k log x over A. Of course, both k and A vary with the temperament, the health, the habits, and the social surroundings of each individual. Laplace gives to x the name fortune physique, and to y the name fortune morale. Bernoulli himself seems to have thought of x and A as representing certain amounts of property rather than of income. But we cannot estimate the property necessary for life without some understanding as to the length of time during which it is to support life, that is, without really treating it as income. Perhaps the guess which has attracted the most attention after Bernoulli's is Kramer's suggestion that the pleasure afforded by wealth may be taken to vary as the square root of its amount. Note 9. The argument that fair gambling is an economic blunder is generally based on Bernoulli's or some other definite hypothesis. But it requires no further assumption than that firstly, the pleasure of gambling may be neglected, and secondly, phi double dash of x is negative for all values of x, where phi of x is the pleasure derived from the wealth equal to x. For suppose that the chance that a particular event will happen is p, and a man makes a fair bet of py against 1 minus py that it will happen. By so doing he changes his expectation of happiness from phi of x to p phi of x plus 1 minus py plus 1 minus p phi x minus py. This, when expanded by Taylor's theorem, becomes phi of x plus half of p by 1 minus p squared y squared phi double dash of x plus theta by 1 minus p by y, plus half of p squared by 1 minus p by y squared by phi double dash by x minus theta py, assuming phi double dash of x to be negative for all values of x. This is always less than phi of x. It is true that this loss of probable happiness need not be greater than the pleasure derived from the excitement of gambling, and we are then thrown back upon the induction that pleasures of gambling are, in Bentham's phrase, impure, since experience shows that they are likely to engender a restless, feverish character, unsuited for steady work as well as for the higher and more solid pleasures of life. Note 10. Following on the same lines as in Note 1, let us take V to represent the disutility or discommodity of an amount of labour L. Then the differential of V over the differential of L measures the marginal degree of disutility of labour, and, subject to the qualifications mentioned in the text, the square of the differential of V over the differential of L squared is positive. Let M be the amount of money or general purchasing power at a person's disposal. Mu is the total utility to him, and therefore the differential of mu over the differential of M its marginal utility. Thus, if delta W be the wages that must be paid to him to induce him to do labour delta L, then delta W by the differential of mu over the differential of M equals delta V, and the differential of W over the differential of L multiplied by the differential of mu over the differential of M equals the differential of V over the differential of L. If we assume that his dislike to labour is not a fixed but a fluctuating quantity, we may regard the differential of W over the differential of L as a function of M, V and L, and then both the square of the differential of W over the differential of M by the differential of L and the square of the differential of W over the differential of V by the differential of dl are always positive. Note 11. If members of any species of bird begin to adopt aquatic habits, every increase in the webs between the toes, whether coming about gradually by the operation of natural selection or suddenly as a sport, will cause them to find their advantage more in aquatic life, and will make their chance of leaving offspring depend more on the increase of the web. So that if the function of t be the average area of the web at time t, then the rate of increase of the web increases, within certain limits, with every increase in the web, and therefore f" of t is positive. Now we know by Taylor's theorem that the function of t plus h equals the function of t plus hf' of t plus the square of h over 1.2 by f" t plus theta h. And if h be large, so that h squared is very large, then the function of t plus h will be much greater than the function of t, even though f' of t be small and f" of t is never large. There is more than a superficial connection between the advance made by the application of the differential calculus to physics at the end of the 18th century and the beginning of the 19th, and the rise of the theory of evolution. In sociology as well as in biology, we are learning to watch the accumulated effects of forces which, though weak at first, get greater strength from the growth of their own effects, and the universal form, of which every such fact is a special embodiment, is Taylor's theorem. Or, if the action of more than one cause at a time is to be taken account of, the corresponding expression of a function of several variables. This conclusion will remain valid even if further investigation confirms the suggestion made by some Mendelians that gradual changes in the race are originated by large divergences of individuals from the prevailing type. For economics is a study of mankind of particular nations, of particular social strata, and it is only indirectly concerned with the lives of men of exceptional genius or exceptional wickedness and violence. Note 12. If, as in Note 10, V be the discommodity of the amount of labour which a person has to exert in order to obtain an amount X of a commodity from which he derives a pleasure U, then the pleasure of having further supplies will be equal to the pain of getting them when the differential of U over the differential of X equals the differential of V over the differential of X. If the pain of labour be regarded as a negative pleasure, and when we write U is congruent to minus V, then the differential of U over the differential of X plus the differential of U over the differential of X equals 0, i.e. U equals U equals a maximum at the point at which his labour ceases. Note 12 bis. In an article in the Giornali degli Economisti for February 1891, Professor Edgeworth draws a diagram which represents the cases of barter of apples for nuts. Apples are measured along OX and nuts along OY. OP equals 4, PA equals 40, and A represents the termination of the first bargain in which 4 apples have been exchanged for 40 nuts, in the case in which A gets the advantage at starting. B represents the second and C the final stage of that case. On the other hand, A' represents the first and B'(C')D' the second, third and final stages of the set of bargains in which B gets the advantage at starting. QP, the locus on which C and D' must both necessarily lie, is called by Professor Edgeworth the contract curve. Following a method adopted in his Mathematical Psychics, 1881, he takes capital U to represent the total utility of capital A of apples and nuts when he has given up X apples and received Y nuts, V the total utility of B apples and nuts when he has received X apples and given up Y nuts. If an additional delta X apples are exchanged for delta Y nuts, the exchange will be indifferent to A if the differential of capital U over the differential of X by delta X plus the differential of capital U over the differential of Y by delta Y equals 0, and it will be indifferent to B if the differential of V over the differential of X by delta X plus the differential of V over the differential of Y by delta Y equals 0. These therefore are the equations to the indifference curves OP and OQ of the figure respectively, and the contract curve, which is the locus of points at which the terms of exchange that are indifferent to A are also indifferent to B, has the elegant equation: the differential of capital U over the differential of X divided by the differential of capital U over the differential of Y equals the differential of capital V over the differential of X divided by the differential of capital B over the differential of Y. If the marginal utility of nuts be constant for A and also for B, the differential of capital U over the differential of Y and the differential of capital V over the differential of Y become constant. Capital U becomes phi of A minus X plus the change in Y, and V becomes psi of A minus X plus beta Y, and the contract curves becomes function of X equals 0 or X equals C, that is, a straight line parallel to OY, and the value of delta Y to delta X given by either of the indifference curves, a function of C, thus showing that by whatever route the barter may have started, equilibrium will have been found at a point at which C apples have been exchanged, and the final rate of exchange is a function of C, that is, it is a constant also. This last application of Professor Edgeworth's mathematical version of the theory of barter to confirm the results reached in the text was first made by Mr. Berry and is published in the Giornali degli Economisti for June 1891. Professor Edgeworth's plan of representing U and V as general functions of X and Y has great attractions to the mathematician, but it seems less adapted to express the everyday facts of economic life than that of regarding, as Jevons did, the marginal utilities of apples as functions of X simply. In that case, if A had no nuts at starting, and is assumed in the particular case under discussion, U takes the form phi1 of A minus X by the differential of X for values between 0 and X, plus psi1 of Y by the differential of Y for values between 0 and Y, similarly for V, and then the equation to the contract curve is of the form phi1 of A minus X divided by psi1 of Y equals phi2 of X divided by psi2 of B minus Y, which is one of the equations of exchange in Jevons' theory. Note 13. Using the same notation as in Note 5, let us take our starting point as regards the time at the date of beginning to build the house, and let capital T' be the time occupied in building it. Then the present value of the pleasures which he expects to derive from the house is H equals pi r to the minus t by the differential of h over the differential of t by the differential of t for values between t' and t. Let delta v be the element of effort that will be incurred by him in building the house in the interval of time delta t, between the time t and the time t plus delta t. Then the present value of the aggregate of effort is v equals r to the minus t by the differential of v over the differential of t by the differential of t for values between 0 and t'. If there is any uncertainty as to the labour that will be required, every possible element must be counted in, multiplied by the probability pi' of its being required, and then V becomes pi r to the minus t by the differential of v over the differential of t by the differential of t for values between 0 and T'. If we transfer the starting point to the date of the completion of the house, we have h equals pi r to the minus t by the differential of h over the differential of t by the differential of t for values between 0 and t1, and v equals pi r to the t by the differential of v over the differential of t by the differential of t for values between 0 and t', where t1 equals t minus t'. And this starting point, though perhaps the less natural from the mathematical point of view, is the more natural from the point of view of ordinary business. Adopting it, we see v as the aggregate of estimated pains incurred, each bearing on its back, as it were, the accumulated burden of the weightings between the time of its being incurred and the time when it begins to bear fruit. Jevons's discussion of the investment of capital is somewhat injured by the unnecessary assumption that the function representing it is an expression of the first order, which is the more remarkable as he had himself, when describing Gosson's work, pointed out the objections to the plan, followed by him and Whewell, of substituting straight lines for the multiform curves that represent the true character of the variations of economic quantities. End of Part 1.